Today, we're going to talk about something that sounds almost impossible. We're talking about the Yettinahole Project in India, an incredibly ambitious plan to capture monsoon floodwaters and then somehow lift them over an entire mountain range. So how on earth did they do it?
Right, it sounds like something out of mythology, but it's a very real, very complex engineering challenge. So in this explainer, we're going to follow the incredible journey of that water through one of India's most massive infrastructure projects to answer that exact question.
So our story starts right here, in the lush Western Ghats. Now, this is a biodiversity hotspot, and during the monsoon season, it gets absolutely drenched with rain. This creates a huge surplus of water that for the longest time just flowed right into the Arabian Sea, totally unused.
But the mission of this project is to change all that. The idea is to capture that surplus water and send it hundreds of kilometers east to regions like Kolar, places that are often stricken by drought. I mean, it's desperately needed there, not just for drinking water, but to replenish the groundwater itself.
Okay, so where do you even begin with something this huge? Well, the very first and maybe the most colossal challenge is just collecting all that water and then somehow getting it over the massive physical barrier of the mountains. Really, the only way to go is up. The collection part is actually surprisingly delicate. You might think they'd build one giant dam, but that's not it at all. It starts with 8 precisely placed weirs, which are basically just low dams, and they're built across 4 different streams.
And here's the clever part. These weirs don't actually stop the rivers. They're designed to just skim off the excess floodwater during the monsoon season. They funnel that extra water into the project's main arteries, all while letting the river's normal base flow continue right on its natural path.
And now we get to the really mind-boggling part. The water has to be lifted over 230 meters vertically. To put that in perspective, that's like pumping an entire river to the top of a 60-story skyscraper. It's just an insane amount of vertical lift.
So how in the world do they pull that off? Well, this monumental lift is done in stages. First, the water gets channeled into these huge pump houses. Then, massive, powerful pumps force it into these pressurized steel pipelines they call raising mains. You could almost think of them as giant straws, just pushing the water straight uphill.
This right here, this is the first major leg of the journey. You can see the water being pushed from the weir, it goes through that pump house, and then it's forced up the raising main, literally conquering the mountain's elevation. It's just a perfect example of engineered power overcoming natural geography.
Okay, so once the water finally reaches the top of that mountain ridge, its entire journey transforms. The brute force of all that pumping gives way to the gentle but unstoppable pull of gravity.
For the next 274 kilometers, let that sink in. 274 kilometers. The water gets to enjoy a much calmer ride. It flows through this massive gravity canal, which is basically a man-made river snaking its way across the landscape.
So what exactly is a gravity canal? Well, it's pretty much what it sounds like, a man-made river. But it's engineered with an incredibly precise, very gentle downward slope, and that tiny incline is all that's needed to keep all that water flowing for hundreds and hundreds of kilometers. No more pumps needed. And the scale of this concrete river is just immense. I mean, look at it. It's a real testament to the sheer volume of construction, but also to the incredible precision engineering you need to maintain that perfect gravitational slope over such a huge distance.
So, after this incredible journey, the water doesn't just stop at one final destination. Nope, it enters a really complex distribution network. It's like a web of canals and tunnels, all designed to deliver this precious resource to the people who need it the most.
First things first, all the water arrives at this massive reservoir. It acts as a central holding tank and the main distribution hub for everything that comes next. And when I say massive, I mean it. It holds a staggering amount of water, enough to fill over 65,000 Olympic-sized swimming pools.
From that one giant reservoir, an enormous spiderweb of smaller feeder canals and tunnels just branches out in all directions. And we're talking about a serious network here. Over 630 kilometers of canals and more than 30 kilometers of tunnels, all fanning out to reach countless towns and tanks.
And this intricate system, this is the whole point of the entire project. It's designed specifically to deliver drinking water and to recharge those depleted groundwater tables across dozens and dozens of regions in Karnataka's absolute driest districts.
You know, that 274-kilometer path for the main canal, it wasn't exactly a clear, empty runway through the countryside. The engineers had to figure out how to navigate a landscape that was already filled with all kinds of major obstacles.
I mean, the canal's path had to deal with a whole list of barriers. It had to cross a major river, a busy railway line, a national highway, and it even had to pass through a protected reserve forest. And every single one of these required a completely unique engineering solution.
And these crossings, they weren't just an afterthought. They were fundamental challenges that had to be solved from day one. You can see right here in the project plans, they explicitly label how this conveyance system has to go over, under, or around all these critical pieces of existing infrastructure.
So how do you get your canal across a river? Well, you build a modern-day aqueduct, basically a water bridge. To get the canal across rivers and deep valleys without losing that all-important gravitational flow, engineers built 12 of these major aqueducts, literally carrying their concrete river through the air.
And that brings up a really crucial point. This project isn't just one long canal. It is a complex system of 636 different structures. We're talking everything from aqueducts and bridges to culverts and regulators, all having to work together in perfect harmony.
So I think the key takeaway here is this. From that initial massive lift to the long, slow gravitational flow, all the way to that final distribution network, every single component is a critical link in the chain that makes this water's incredible journey possible. You know, the Yettinahole Project is a powerful and, to be sure, controversial example of human ingenuity being pushed to its absolute limits to solve a water crisis. And it really makes you wonder, doesn't it, as our climate continues to change and water becomes ever more precious, what other impossible engineering feats are going to become necessary?